It is the early hours of June 9, 1944, and over the Loire Valley in occupied France, 19 Avro Lancasters are climbing towards 8,000 feet in the darkness. Below them lies the small town of Saumur, and beneath that, cut through solid limestone, runs a railway tunnel 1,000 yards long. Inside that tunnel, German commanders believe, lies the answer to a desperate problem. A Panzer division must reach the Normandy beachhead, where Allied troops have been ashore for barely 3 days, and the tunnel is the fastest route south to north. The bomber crews circling above do not know all of this. They know only that they are carrying something nobody has dropped in combat before: a sleek, finned bomb taller than 2 men standing on each other's shoulders, weighing as much as a family car. Wing Commander Leonard Cheshire dives his Mosquito to 500 feet to mark the target with precision flares, and one by one the Lancasters release their loads. A single bomb bores clean through the hillside, drops 60 feet through solid rock, and detonates inside the tunnel itself. The line is severed. The Panzers never arrive in time. Not one British aircraft is lost. The bomb is called Tallboy, and on this night it works exactly as its eccentric, brilliant designer intended. What follows is the story of how a single British engineer, working largely alone against the skepticism of his own government, built a weapon that could do what thousands of conventional bombs could not: break open the most heavily fortified structures the Third Reich had ever built. This is the story of the bomb that turned solid ground into a weapon, sank Hitler's mightiest battleship, and rewrote the rules of what aerial bombardment could achieve. By 1943, Bomber Command had a problem that no amount of additional aircraft could solve. Germany had spent years pouring concrete. Submarine pens at Saint-Nazaire sat beneath roofs of reinforced concrete more than 8 meters thick. The V-weapon storage complex known as La Coupole, buried into a chalk hillside near Saint-Omer, was capped by a dome of concrete weighing 55,000 tons. The Blockhaus had walls 7 meters thick. Viaducts carrying vital rail traffic into the industrial Ruhr were built to withstand exactly the kind of bombing the RAF had been throwing at them for years. Against these targets, the standard tools of Bomber Command were simply the wrong instrument for the job. A typical 1,000-pound bomb, even dropped with reasonable accuracy, would explode against the outer skin of a structure like this and achieve almost nothing. The casing was too thin to survive the impact of striking concrete or hard ground at speed, so the bomb tended to shatter or detonate on the surface, throwing its blast harmlessly outward into the air rather than into the target. Raid after raid against the U-boat pens on the French coast had demonstrated the futility of the approach. Bombers returned, crews reported direct hits, and reconnaissance photographs the next morning showed roofs scarred but intact, the pens beneath untouched, the submarines inside undamaged and ready to sail again. Meanwhile, the cost in aircrew was severe, since flying repeatedly over heavily defended ports and railheads to drop weapons that achieved little was by any measure a poor trade. Crews flying these missions understood the arithmetic better than anyone. A bombing run over a defended port or rail junction exposed an aircraft and its 7-man crew to anti-aircraft fire, searchlights, and night fighters for the better part of an hour, and doing so repeatedly against a target that simply would not yield was, by any reasonable measure, an unsustainable use of men and machines. Some estimates from the period suggested that fully half of all bombs aimed at hardened concrete targets achieved no meaningful structural effect whatsoever, scattering harmlessly across roofs built specifically to absorb exactly that kind of punishment. Something had to change, not merely in scale, but in kind. The deeper issue was conceptual as much as mechanical. Most bomb design assumed that destruction came from blast and fragmentation spreading outward through the air, hitting whatever stood nearby. Barnes Wallis, the aeronautical engineer already well known within Vickers-Armstrongs for his work on airship structures and the Wellington bomber, believed this assumption was fundamentally wrong for hardened targets. He argued, in a 1941 paper modestly titled "A Note on a Method of Attacking the Axis Powers," that the real destructive power of a very large explosion came not from the air blast at all, but from the shock wave it sent through solid ground. Detonate a sufficiently large charge close to, or ideally beneath, a structure's foundations, Wallace reasoned, and the Earth itself would do the work, transmitting a seismic shock far more efficiently than air ever could. He called the concept the earthquake bomb. The trouble was that nobody in the Air Ministry believed an aircraft existed, or could be built in time, that was capable of carrying a bomb large enough to make the theory work. Wallace initially envisioned something in the region of 10 tons. The bomber he proposed to carry it, a 50-ton aircraft he named the Victory Bomber, flying at 320 miles an hour at 45,000 feet, was politely but firmly rejected. For a man convinced he had found the solution to Bomber Command's hardest targets, it must have felt as though the impossible problem of German fortifications had simply been replaced by an equally impossible problem of British engineering. The breakthrough came only after the Dambusters raid of May 1943, when the success of Wallace's earlier bouncing bomb against the Möhne and Eder dams persuaded skeptical officials that his unconventional thinking was worth backing again. Sir Wilfrid Freeman at the Ministry of Aircraft Production pushed the earthquake bomb concept forward, but with a practical compromise. No aircraft existed capable of carrying 10 tons, so Wallace scaled his design down to 12,000 pounds, roughly 5.5 tons, and the project was authorized under the deliberately bland codename Tallboy. The finished weapon, built at Vickers Armstrong's Brooklands facility near Weybridge in Surrey, was 21 feet long and just over 3 feet in diameter at its widest point, about the size of a small family saloon car stood on its end. Roughly 5,200 pounds of that weight was Torpex, an explosive around 50% more powerful than TNT, made more effective for this purpose by the inclusion of aluminium powder, which extended the duration of the explosion and produced a longer, harder pulse to transmit through the ground. What made Tallboy genuinely revolutionary, though, was not the explosive, but the casing wrapped around it. Forged from hardened steel up to 4 inches thick at the nose, the casing was designed to survive the violence of striking concrete, rock, or packed earth at extraordinary speed without shattering, buying the bomb the crucial seconds it needed to bury itself before detonating. Because each casing had to be individually cast and machined to withstand these forces, Tallboy could not be mass-produced on an assembly line the way an ordinary bomb could. Each one was effectively hand-finished in small batches, a fact that limited how quickly Bomber Command could build up its stocks. Aerodynamically, the bomb was shaped almost like an oversized artillery shell, with offset tail fins that imparted a slow spin as it fell, stabilizing its flight and improving accuracy in a way no earlier British bomb had managed. Dropped from around 20,000 feet, it reached a terminal velocity faster than the speed of sound, somewhere in the region of 3,600 to 3,700 feet per second, hitting the ground with such force that, against open earth, it carved a crater roughly 80 feet deep and 100 feet across, displacing close to 1 million cubic feet of soil. To put that figure into more ordinary terms, filling that crater back in again would have taken something like 5,000 tons of earth. To make sure the bomb actually exploded rather than burying itself uselessly, engineers fitted not 1 but 3 separate long-delay fuses, so that even if 2 failed, the third would still trigger detonation, with the delay adjustable from as little as 30 seconds to as much as 30 minutes after impact, depending on whether the target was a tunnel roof or something buried far deeper. If you are finding this interesting, a quick subscribe helps more than you know. The aircraft tasked with carrying this monster needed modification, too. Only specially adapted Avro Lancasters could manage it. Fitted with bulged bomb bay doors to clear the bomb's fins, strengthened bomb hooks, and, for crews of No. 617 Squadron, the stabilizing automatic bomb sight, a far more precise instrument than the standard equipment used elsewhere in Bomber Command, though one that demanded clear visual identification of the target and a great deal of practice to use well. Saumur was only the beginning. Through the summer of 1944, Tallboys fell on V weapon storage depots, on the fortified dome at Wizerns, where one bomb shifted the entire 55,000-ton concrete structure out of alignment, and on U-boat pens along the French coast. At Brest, 15 Lancasters of 617 Squadron scored 6 direct hits, with bombs actually penetrating the concrete roofs that had shrugged off years of conventional bombing. At Le Havre and Boulogne, Tallboys against E-boat pens forced the German vessels to relocate to less convenient harbors, disrupting operations against the Allied invasion fleet, even where the pens themselves were not destroyed outright. Records from these raids vary in completeness. Some attacks are documented in precise detail through Royal Air Force operational logs and post-war photographic reconnaissance, while the exact extent of damage to certain heavily classified or remote targets remains harder to establish even today. No use of the weapon, though, captured public imagination quite like its role against the German battleship Tirpitz, sister ship to the Bismarck, and at over 50,000 tons, one of the largest and most heavily armored warships ever built. For years, Tirpitz had tied down a disproportionate share of British naval strength simply by existing, moored in Norwegian fjords as a permanent threat to Arctic convoys. Conventional attacks, including a daring raid by Royal Navy midget submarines, had damaged but never destroyed her. In September 1944, flying from a forward base in northern Russia, Lancasters of 9 and 617 squadrons struck her with a single tallboy that tore through her bow, leaving her unseaworthy. An attempt to finish the job in late October failed when cloud obscured the target at the critical moment. Then, on November 12, 1944, 32 Lancasters took off from airfields in northern Scotland and flew a route of more than 2,000 miles, crossing neutral Swedish airspace to approach Tromsø from an unexpected direction. The weather held clear. Wing Commander Willie Tate's aircraft released the first tallboy at 9:41 in the morning, and within minutes the battleship had taken at least 2 direct hits and several damaging near misses. Tirpitz capsized within 20 minutes, and somewhere between 940 and 1,200 of her crew lost their lives. Not a single British aircraft was lost in the attack. It is worth comparing this against what else existed at the time. Germany possessed nothing equivalent. Luftwaffe bombers carried nothing close to Tallboy's weight or penetrative power, and German fortification doctrine instead simply kept building thicker concrete, an arms race in which Tallboy proved that no amount of additional thickness could fully compensate for a weapon designed to attack from underneath rather than from the side. The closest American counterpart, the 12,000-pound T-10, never reached operational use in the war in anything like Tallboy's numbers, and the United States Army Air Forces relied instead on sheer quantity, sending hundreds of conventional bombs against a target in the hope that enough would eventually find their mark. It worked after a fashion, but at far greater cost in aircraft, crews, and time. By contrast, where Tallboy achieved a result, it often did so in a single sortie with a handful of aircraft, a difference that mattered enormously to the men who had to fly the missions. Roughly 850 tallboys were used during the war, and the basic earthquake principle later inspired American adoption of similar deep penetration concepts in the decades that followed, though direct lineage to any specific post-war weapon remains a matter of some debate among historians. Wallace was not finished. In early 1945, a still larger weapon entered service, the 22,000-pound Grand Slam, originally codenamed Tallboy Large until journalists got hold of the smaller bomb's name and the larger weapon needed a new one. Grand Slam was 26.5 feet long, its hardened casing cast as a single piece around a concrete core, and it remains, to this day, the largest conventional bomb ever used in combat by any Air Force. On March 14, 1945, Squadron leader Jock Calder dropped the first Grand Slam used in anger against the Bielefeld railway viaduct in Germany, and the earthquake effect brought down 100 meters of the structure even though the bomb itself landed some distance away. Weeks later, Grand Slams were used against U-boat pens at Farge, near Bremen, where 2 bombs penetrated more than 7 meters of reinforced concrete before exploding, bringing down the entire ceiling of the structure in a single attack. The honest assessment of Tallboy's legacy sits somewhere between 2 extremes. It was not, on its own, a war-winning weapon, and historians are careful to note that broader strategic bombing campaigns, ground operations, and the simple exhaustion of German resources all mattered more to the war's outcome than any single munition. But within its narrow purpose, against the specific category of target that no other Allied weapon could touch, Tallboy was simply without equal. It demonstrated, conclusively, that earthquake bombing worked as Wallace had theorized, that the ground itself could be turned into a delivery mechanism for destruction against structures designed to be impervious to attack from above. Fewer than 1,000 stabilizing automatic bomb sights were ever manufactured, a reminder of just how specialized and limited the whole program remained even at its height, restricted largely to the handful of squadrons trained and equipped to use it. Several Tallboys remain unaccounted for even now. One was discovered unexploded during dam repairs in 1958, and another, remarkably, was found off the Polish coast near Świnoujście as recently as 2020, a silent reminder of a weapon that, 80 years on, still occasionally resurfaces. Examples survive today. A Tallboy casing can be seen at the Royal Air Force Museum, and the Imperial War Museum holds extensive photographic records of the Saumur and Tirpitz raids, while wreckage of the great battleship herself still lies, broken up over the decades that followed, in the waters off Tromsø. Return for a moment to that night over Saumur, to 19 aircraft and a tunnel cut through limestone, to a weapon nobody had dropped before, and a problem that had defeated every conventional solution thrown at it. What Barnes-Wallis built was not, in the end, simply a bigger bomb. It was a different idea entirely, that the most heavily fortified place on Earth could be beaten not by attacking its strength directly, but by going underneath it, by letting the ground itself carry the blow. Thick concrete had been Germany's answer to bombing. Tallboy was Britain's answer to thick concrete. Where conventional bombs bounced off, Tallboy bored through. Where massed raids failed for years, a handful of aircraft on a single night sometimes succeeded outright. The submarine pens stood for years against everything thrown at them, until they did not. The viaducts carried German trains for years, until they could not. The Tirpitz sat in her fjord for years, a threat simply by existing, until 20 minutes ended it for good. Barnes-Wallis had been told his idea was impossible, told the aircraft to carry it would never be built, told to scale back his ambitions again and again. He did, and it still worked. That, in the end, is the story of Tallboy. Not the biggest weapon of the Second World War, not the most numerous, but very possibly the one that most completely solved the precise problem it was built to solve. Germany built walls it believed nothing could break. Britain built a bomb that did not need to break them at all. It simply went underneath and let the earth do what no wall could survive,